All right, let's continue talking about systems of linear equations and the different methods we have for solving them. So last time we saw that one method we have for solving these is graphing. But the thing with graphing is that it isn't always accurate. And so let's take a look at why that is. So if we take a look at this system here, let's say we have this graph here. And I'm just going to roughly draw this one because we're not actually going to solve it. But let's say we have the line y equals 2x plus 1. So that's going to go through 1, and then it'll go up 2 over 1, up 2 over 1, somewhere over here, and then we have our line going through those points. So this is y equals 2x plus 1. And then let's also say we have the line y equals negative 3x minus 1. So negative 3x minus 1 is going to go through negative 1, and we're going to go down 3 over 1. So down 1, 2, 3 over 1. And it's going to roughly go somewhere along here. And this is y equals negative 3x minus 1. So you don't have to copy this one down. We're not focused on the solution. The important thing to note here is that the intersection of these 2 points, or these 2 lines, sorry, is right here. And it's not at a whole number. It's somewhere, the x is somewhere between 0 and negative 1. The y is somewhere between 0 and 1. It's not easy to tell if maybe our graphing was inaccurate and it should be at a whole number. Or maybe the solution for this one is a fraction. And when we're graphing, it's hard to tell exactly where that solution is. Let's say the solution was negative 1/2, 1/4. We can guess that it is that, but we don't know for sure when we're graphing. And so since the solution is not always a whole number, just like when you're solving regular equations, you can end up with fractions. A whole number ordered pair. Since we don't always have a whole number ordered pair as our solution, it's hard to tell where those fractions are. So one of these first methods that we're going to use is substitution. Now we're going to be doing exactly like what it sounds. We're going to be doing some substituting. And then in the next section, we'll talk about elimination or addition. It's 2 different names for that one. So let's first write out the steps for solving with substitution. And these steps almost make it sound more complicated than it is, so don't get kind of wrapped up in these steps. We'll write them out just so you have them, and then we'll focus more on the examples. All right, so first thing we want to do is solve one equation, just one of them, for one variable. And it doesn't matter which one you solve for, sometimes one is easier than the other. If one doesn't have a coefficient other than 1, then it's going to be easiest to solve for that variable. We'll see that a little bit more. And then whatever we get from that, we're going to plug the expression for that variable into the other equation. So make sure you're not plugging it back into the same equation, otherwise you'll just get a true statement, which is going to actually tell us something specific in our special cases. Number 3, at this point we're going to have one equation with one variable. So we can solve that just like a regular equation. So we're going to solve the equation from step 2. And then lastly, well, second to last, we're going to plug the value back into either equation. And by either equation, I mean either of the 2 original equations where it has both an x and a y, to find the value of the other variable. So solving the equation from step 3 is going to give you, let's say, x, and then you'll plug it back in to find y. And then once you have this, you can check your solution like always. And just like we talked about checking for the graphing method, you still have to do the same check where you plug that x-y pair into both of your original equations. So remember, a system solution or a solution to a system has to be a solution to both. If it's a solution to one or the other, either check your arithmetic or try resolving it, because doing it this way, you will get a solution unless you have one of the 2 special cases, which that's going to look a little bit different. All right, let's go ahead and jump into some examples. And so for these ones, we're explicitly told to solve by substitution. So again, if they tell you explicitly how to solve it, make sure you use that method, especially in the homework, because you want to get practice with all of these. But on the exam, if it just says substitution or elimination, which it'll usually do because it wants you to be able to figure out which one's the best method, pick whichever one you think is best in that situation, and we'll kind of talk about when to use one over the other. Most of the time we just don't use graphing because it's so inaccurate. All right, number 1, 3x plus 5y equals 69 and y equals 4x. All right, so for this one, in order to use substitution, we want one variable in one of the equations to be by itself. So this one is actually a perfect one for substitution because this y is already by itself. So what we're going to do is we're going to substitute. So we're going to take the fact that y is equal to 4x, and so we're going to replace y in our other equation with 4x. We're going to substitute it in, and then I'm going to replace this first equation with our new equation where we substitute this in. So this becomes 3x plus 5 times, and a really good habit to start to get into is with the parentheses here. So if we had some addition or subtraction in this y expression here, you want to make sure that that's always in parentheses so we know to distribute. So I'll go ahead and put this 4x in parentheses. So the only thing I've done here is taken this y, changed it to 4x. Everything else stays the same, so it's still equal to 69. And we're just kind of ignoring this second equation now because we've kind of combined them into 2. And now let's go through and solve this one. So this was step 2. Step 1 was solving for y, which we didn't have to do. But now step 3 is solving. So let's take 3x plus 20x equals 69. Combine these, so 23x equals 69. Divide both sides by 23. And we get x equals 3. And so this is our first part of the solution. But remember, when you're looking for the solution for these, you're looking for the point where they intersect. So you need both the x and the y. And so if you only put the x, that would be half of the solution. So now we're going to do step 4, and we're going to take this x, plug it back into either equation. So what I mean by that is we're going to take this right here, plug it back into either one of these. Usually one of them is going to be a little bit nicer to work with. This bottom one is super nice because the y is already by itself. So let's go ahead and take this, plug it into y equals 4x. So we get y equals 4 times 3, so y equals 12. And a lot of the time for your solutions for these, depending on how MyMathLab has it set up, normally they'll have you type as an ordered pair. So our solution is the 0.312. And that's it. We don't have to go through graphing this one. We have the point where these two lines intersect. And again, if you wanted to check it, you're going to take this point, plug it into your two equations that you started with, and make sure they're both true statements when you simplify. Let's try another one. 2x plus 7y equals negative 12. And x equals 3 minus 2y. So again, first step is already done for us. Our x is already by itself. So I'm going to go ahead and take our expression for x, substitute it in for x in our other equation. So this one now becomes 2 times 3 minus 2y plus 7y equals negative 12. And then we'll simplify and solve. So let's distribute. So we get 6 minus 4y plus 7y equals negative 12. Combine like terms. So we get 6 plus 3y equals negative 12. Subtract 6 from both sides. So we get 3y equals negative 18. Divide both sides by 3, and we get y equals negative 6. So we have part of our solution, and now we want to take this negative 6 and plug it back into either of these equations. I'm going to go ahead and plug it into x equals 3 minus 2y. It's a little bit nicer to solve, but again, either one works. So we get x equals 3 minus 2 times negative 6. So x equals 3 minus negative 12. And then if we add the opposite, we get 15. So our solution as an ordered pair is the point 15, negative 6. So that's where these two lines intersect. All right, now let's try one that's a little bit more complicated. We have to actually do step 1. So we're given x plus 4y equals negative 1, and 2x minus 5y equals 11. So now for this one, you want to think, first of all, if we don't have an equation with x or y by itself, we need to solve for x or y first. And we want to figure out which one's easiest to solve for. So now if we look at the x's, we have an x and a 2x. The y's, we have a 4y and a 5y. If they have a coefficient other than 1, it's going to give you fractions if you try to solve for it most of the time. So we're going to have to divide by 4 in this first equation for y, or divide by 2 or 5 in the second equations. So if we solve for x in this first equation, we're not going to have to divide by anything. So I'm going to just bring this one over here. And all I'm going to do is subtract 4y from both sides. And it technically doesn't matter which order you put these in. I'm going to stick to the same order that we've been doing for graphing, just so you stay in that habit. So negative 4y minus 1. Once you have that x by itself, you're going to take that expression and plug it into the other equation for x. Make sure it goes in the other one. And now we can go ahead and actually plug that in. So we have 2 times negative 4y minus 1 minus 5y equals 11. And then we'll distribute and solve. So we get negative 8y minus 2 minus 5y equals 11. Combine, so negative 13y minus 2 equals 11. Add the 2. So I'm going quite a bit faster through solving these because hopefully you should have a lot of practice with this by now. Negative 13y equals 13. Divide both sides by negative 13. And we get y equals negative 1. All right, so now that we have our y, we're going to take this and we're going to plug it back into either of our equations. Let's go ahead and plug it into this first one just because the x is by itself. So we won't have to divide by anything at the end. So remember, we're looking for x now. So I'm going to plug this into x plus 4y equals negative 1. So we get x plus 4 times negative 1 equals negative 1. So x, 4 times negative 1 is negative 4 equals negative 1. Add 4 to both sides, and we get x equals 3. So our solution here is the point 3, negative 1. And one thing to note is that once you have this y here, I plugged it into this first equation that we had. We could have also plugged it into this one where we'd solved for x. That's just because this is the same as the first equation, just rearranged. That would have been a little bit nicer actually to plug back into this one. But just to kind of stick to the same process, I'm going to stick to plugging it into one of the first equations. But just keep that in mind. If you want to go straight to plugging it into this rearranged one, that's perfectly fine. Make sure you don't plug it back into the one that you just solved because that'll just give you a true statement. All right, let's try another one of these before we take a look at some special cases. So number 4, let's try 2x plus 5y equals 4, and x plus y equals negative 1. So for this one, again, you're looking to solve for x or y. Try to think right now which one you would be better to solve for, and there's actually no right answer here. In terms of x or y, there is a better equation. So this first one, we have variable or coefficients for the x and the y. In the second one, our coefficients are both 1. So we're going to solve for x or y in the second equation. So I'll go ahead and solve for y. So I'll go ahead and subtract x. This is just to show you that you can solve for either one. It doesn't have to be x. So we get y equals negative x minus 1. And then we're going to take this, plug it into our other equation for y. So we have 2x plus 5 times negative x minus 1 equals 4. Distribute, so we get 2x. 5 times negative x is going to be negative 5x. 5 times negative 1 is negative 5 equals 4. Combine, so negative 3x minus 5 equals 4. Add the 5 to both sides. So negative 3x equals 9. And divide both sides by negative 3. So we get x equals negative 3. And then I'm going to plug this back in to either one of these equations. The second one's a lot nicer because there's only an x and a y. There's no other coefficients. So I'll plug it into x plus y equals negative 1. So we have negative 3 plus y equals negative 1. Add 3 to both sides. And we get y equals 2. So our solution here is negative 3, 2. All right, now let's take a look at one of our special case solutions and what this is going to look like. These ones are actually really nice and short because they're a special case solution. So we're given 8x minus 2y equals 1, and y equals 4x minus 8. So we're given a nice one because our y is already by itself. So I'm going to take the 4x minus 8, substitute it in for y in that first equation. So we get 8x minus 2 times 4x minus 8 equals 1. 8x distribute minus 8x, negative 2 times negative 8 is positive 16 equals 1. And now at this point you should notice something a little different, and this is exactly what we saw with just one linear equation with this type of solution. 8x minus 8x gives us 0, so those cancel out and we're left with 16 equals 1, which is not true. So if you think back to our special case solutions from before, what kind of solution did we have when we got a full statement like this at the end? We got no solution. And so if you think back to graphing, what kind of lines did we have when we had no solution? We had parallel lines because they never intersect. So this is all related to what we saw in the last section. This is just a different way of solving it. But if you see this false statement here, it means we have no solution. So it makes it pretty fast, so you don't have to go back and substitute it back in. And then if we take a look at our other special case, let's see, 3x minus y equals 4, and negative 9x plus 3y equals negative 12. All right, so this one's a little bit uglier to solve. We're not given an x or a y by itself, but there is one that doesn't have a coefficient other than 1. That's this y in the first equation. So I'm going to take that 3x minus y equals 4 and solve for y. So I'll subtract 3x. So negative y equals negative 3x plus 4. And then change all the signs or divide everything by negative 1, just like if you were going to graph this, get that y by itself. So positive y equals positive 3x minus 4. Now we can take this expression, plug it into our other equation for y. So we get negative 9x plus 3 times 3x minus 4 equals negative 12. Let's distribute, so negative 9x plus 9x minus 12 equals negative 12. You can see a lot of kind of symmetry here. Our 9's x's are going to cancel because they're opposites. So we're left with negative 12 equals negative 12, which is a true statement. So whenever we go through this, the only thing to be careful with these is you can get a true statement if you took this 3x minus 4 and accidentally plugged it into the same equation. That would give you the same result, but that's not because you have this special type of solution. That's because you plugged it back into the wrong one. So be really careful. This only happens when we have an infinite number of solutions. And so again, if we think back to what we saw when we were graphing, when did we have an infinite number of solutions? When we graphed it and we had the same line. So if we were to go through and solve both of these equations here for y, they look different now, but if we solve for y, they would both end up being y equals 3x minus 4. All right, let's go ahead and try two more. These are a little bit trickier because they have fractions and decimals, but we're gonna do what we've seen before and just get rid of them. So our first one here is 3x plus 1/4 y equals 2, and 1/2 x plus 3/4 y equals -5/2. Okay, so I don't want to have to work with all these fractions, especially when we're substituting and solving and doing all of this. So I'm going to go ahead and clear the fractions. And if you think back to, this is all the way back in chapter 2, the way that we had to clear the fractions was we wanted to find the LCD, the least common denominator, for each equation, and then we're going to multiply every single term by the LCD. So if we look at the first equation here, our only denominator is 4. So that's for our first one. And our second one, we have denominators of 2, 4, and 2. So the LCD is also 4. And now we want to multiply every single term by 4. So I'm going to multiply this first one by 4, the second one by 4, this last one by 4, even if it doesn't have a fraction. And we'll do the same thing on the second equation here. So on the first one here, 4 times 3x is 12x. 4 times 1/4, think of this as 4 over 1, and those 4's cancel. So we get 1y, which is just y. And 2 times 4 is 8. Second equation, 1/2 of 4, or if you think about multiplying and reducing, we get 2x. And if you want to still multiply these off to the side, that's perfectly fine. I would just pause and do that now. I'm just going to kind of go through this a little bit faster. Second one here, the 4's cancel, so we get 3 over 1y, or 3y. And then with this last one here, I'll write this one out. 2 and 4 reduced to a 1 and a 2. -5 times 2 is -10. All right, so now we have two new equations that are the same. They're just multiplied by 4, which it still holds the inequality. So now we can go ahead and start using substitution. So let's go ahead and solve this first equation for y. So 12x plus y equals 8. All we have to do is subtract 12x from both sides. And we get y equals -12x plus 8. Now we can take this and substitute it into the other equation for y. So now we have 2x plus 3 times -12x plus 8 equals -10. Let's distribute. So we have 2x minus 36x plus 24 equals -10. Combine, so we get -34x plus 24 equals -10. Subtract the 24. So we have -34x equals -34. And divide both sides by -34. And we get x equals 1. So now if I take this 1 and substitute it back in for x, we can take it and plug it back into one of these original equations. That's going to be kind of ugly because those are all fractions. So I'm going to take it and plug it into one of the ones where we got rid of the fractions. Since we're looking for y, I'm going to plug it into this first one because y is by itself. So I'll take it and plug it into 12x plus y equals 8. So we get 12 times 1 plus y equals 8. 12 times 1 is 12. Subtract the 12. Whoops. And we get y equals -4. So we have the point 1, -4. All right, and let's look at one last case here where we're given decimals. So last one, number 8, we're given 0.2x plus 0.3y equals 0.5, and 0.3x minus 0.1y equals 1.3. So again, I don't want to have to work with decimals the whole time. So I'm going to clear the decimals. And if you remember from chapter 2, we want to multiply by the highest decimal place, which in this one, we have 0.2, 0.3, 0.5, 0.3, 0.1, 1.3. They only have one number in the decimal place, so we can multiply all of these by 10. So let me go ahead and write that in. Multiply by 10, by 10, by 10. Now these all have decimals, but if they didn't all have decimals, you'd still be multiplying everything by 10. And so just remember the trick when you're multiplying by a multiple of 10 is to just move the decimal however many zeros you have. So I'm going to take the decimal on the 0.2, move it to the right. So we get 2x plus 3y equals 5. And then again, 3x minus 1y, so I'll just put y, equals 13. And now this is a lot nicer to work with. So let's go ahead and solve one of our equations for x or y. The nicest one here is going to be this y here because we have just a negative in front. We don't have another number. So let's go ahead and solve this one for y. So we're going to subtract 3x, and we get -y equals -3x plus 13. Divide everything by -1, and we get y equals +3x minus 13. We have y by itself. Let's take that and plug it back into the other equation. So this one up here for y. So we have 2x plus 3 times 3x minus 3 equals 5. Distribute in that 3, and we get 2x plus 9x minus 9 equals 5. So 11x minus 9 equals 5. And I'm just double checking that I wrote these numbers down correctly because we're getting an answer that, let's see. Give me 1 second. Okay, so we multiply by 10, 2x plus 3y equals 5, 3x minus y equals 13. Solve this for y. And, oh, that's why. Okay, so right down here where we were, I think I said negative 13, I wrote negative 3. So make sure this is a negative 13 right here. So it should be a 13 here. And 3 times 13 is 39. All right, so let me fix this 9. Should also be a 39. Add the 39 to both sides. Here we go. So we get 11x equals 44. So if you noticed, what I did was, because I noticed we were going to end up with a really ugly fraction, a lot of the times you can get fractions, they're usually nicer, like a half or a quarter, something like that. We were going to get 14 over 11, which is a really weird fraction to get. So I just wanted to double check that everything was correct. Always a good thing to do when you get weird numbers. All right, so then divide by 11, and we get x equals 4. Take this and plug it back into one of these equations over here. We're solving for y now, so I'm going to plug it into the second one. So 3x minus y equals 13. I keep saying 13 and not writing 13. Here we go. Okay, so 3 times 4 minus y equals 13. 3 times 4 is 12 minus y equals 13. Subtract 12, and we get negative y equals 1, and divide both sides by negative 1. So we get y equals negative 1, which gives us a solution of the point 4, negative 1. All right, so the next time we'll take a look at our last method for solving systems of equations. We'll be looking at elimination.